So we just covered modular arithmetic, and yeah, so if it's -8, -7, -6, and 5, then the remainder is 0, 1, 2, and 3. And similarly, we can keep going. The numbers will always cycle mod 4, 0, 1, 2, 3, 0, 1, 2, 3, and so on. So n and mod 4, the values mod m cycle every m numbers. All right, so the remainders are always 0 through 3. So mod equivalences. There's a reason that the symbol, when we say two numbers are equivalent mod m, is very simple, similar to the equals. And that's because a lot of relations we're familiar with hold in modular arithmetic. So if A is congruent to B mod m and C is congruent to D mod m, then we can add. So we can say A plus C is congruent to B plus D. We can subtract, we can multiply. So A times C is congruent to B times D mod m. So the point is that modular arithmetic works a lot the same way as just regular algebra. And we also have that if A is congruent to B mod m, then you can take it to any power. So A to the n is congruent to B to the n mod m for any n. So for example, if A and B are equivalent mod m, then A squared and B squared are equivalent mod m. A cubed and B cubed are equivalent, and so on. We won't be going through the proofs of these, but as an exercise, you should try and definitely prove the first three. The last one is a bit trickier, but if you follow the definitions, you can figure out all of them. So just try to prove this on your own time.
So actually, the third one implies the fourth one, right? Because you can just keep multiplying itself. And
that's right, Suyash. Yeah. The second one does imply, the third implies the fourth because you can just keep multiplying on. That's right. Yeah. So we're going to think about exponents later, but yeah. All right. So, Alan, you want to? Now we're
Yeah.
going to go through an example.
All right. So one key method when you're doing modular arithmetic problems is when you're looking at, when you want a large number, you can often find a pattern in the small numbers and generalize it like that. So you can sort of cycle them through. So this Amy problem is a really good example of it.
Alan, you want to screen share the slides?
Oh, sure, yeah. Let's do that.
I'll stop the share and Alan will just pick it up in a sec.
So this is a, okay. Sorry about the, so our problem is we have this.
Scroll up a bit to the problem.
Okay, yeah. Sorry, we have this recurrence relation where we can express a n in terms of the last three terms mod 11. So our question here, what we're trying to find a very large, sorry.
If you scroll up one more slide.
Right, yeah. So this is our problem. So we're trying to find a 2018, a 2020, and a 2022. In order to figure out, yeah.
If you guys want to spend 2 or 3 minutes trying to solve it,
right.
we'll give you that, and then after that we'll go.
Right, sorry.
Yeah, no problem. So yeah, just spend 2 minutes trying to solve, 2 or 3 minutes trying to think about this problem a bit, and then Alan will go through the walkthrough.
Yeah, take a look at the tip above it. That's very helpful for this.
Yeah, that's exactly right. Try to think about small cases and patterns. All right, Alan, you want to talk about
Sure,
mod 3?
yeah. So in order to find our large terms, we can look for a pattern in these small terms. So if we have this relation, we want to find a pattern. So let's list out, for instance, the first 10 terms and see what happens. So here we are. We have given the first 3 terms 2, 5, 8. We continue 5, 6, 10, 7, 4, 7, 6. Oh, it's a 2, 5, 8 again. So what that implies is that it's going to actually repeat every 10 terms from 0 to infinity. So
and Alan was able to get these numbers just by just by writing it out by hand. So you have to compute the first 9 just by applying the formula. But after that, you're supposed to notice that 10, 11, and 12 repeat.
Right, yeah. So since as we said, the sequence repeats, basically we have that every term in this sequence can be determined by its units digit. So for instance, a 64 is going to be equal to a 4. So returning to our problem, so we have that this is true. So we find a 2018, a 2020, and a 2022 by looking at a 8, a 0, and a 2. That's going to be 7, 2, and 8. So our answer is 7 times 2 times 8, 112.
Yep. And just to make one part of that a little clearer, the reason that once we got that 3 numbers repeated is that since the recursion, it just requires a recursion. Basically, you can compute one term by computing the previous terms. So if you look at the recursion, you only need the past 3 terms. So since we had 3 of the terms equal, 10, 11, and 12, that means that everything beyond that is simply going to repeat. We don't even have to write down more than that. And then, yeah, like Alan said, it's not exact. You can just determine it by what in this table by taking the period. So a 2018, it's just a8 because if you reduce mod 10, because every 10 it repeats, and a 2020 is going to be a0 because every 10 it repeats, and similarly a 2022 is a8. Does everybody understand this? Some people are raising their hands, I'm seeing. And
yeah, Lokanchu, Nikanch, if you have any questions.
Feel free to unmute and say your question.
Well, I mean, what happens if like term 14 is like 10 and it doesn't actually follow the pattern afterwards?
Oh, so the thing is that since a 10 through 12 are the same as a 0 through 2, we know from that a 13 is going to be the same as a 3 because it relies on those same numbers 2, 5, and 8. So we can sort of extend that pattern to every 10 terms it repeats.
Yeah, we don't even need to think about it afterwards. Since we see that it repeats 3 terms, we know the entire pattern is just going to repeat in that block of 10 every time. Does that make sense?
Okay. Yeah, it makes sense.
And did Lokanshu also have a question? Lokanshu raised his hand.
No, sorry.
Okay. Yeah. Okay. I guess we can.
Yeah, let's continue.
All right. Cool.
So another key idea in modular arithmetic is that of the inverse. That it's depicted a to the -1. So the idea being that a times its inverse is going to be 1. So just like the inverse of 3 in normal numbers would be 1/3, we have, because 3 times 1/3 is 1, we have that the number times its inverse is going to be 1 mod m. So to take so it's one thing that's really important to note here is that this inverse doesn't always exist. To take this example, let's try to find the inverse of 4 mod 6. So in order to do that, let's plug it in. 4 times our inverse is going to be 1. So we need to find x such that 6 is a divisor of 4x minus 1. But an even number can't divide evenly into an odd number, so this x doesn't exist. So you may ask, when does x exist? Well, it turns out there's this really important theorem, and an inverse of A exists only when A is coprime to the modulus. So GCD of A and M is 1. We're not going to be proving that today, but it's really important to know as we go on.
Yeah, the proof is it's not too hard if you understand mods to a pretty good degree, but for this level it may not be very helpful, so we're not going to go over the proof.
Yeah, by the way, another point. So on the inverse is always unique. There's only one. That's important to know.
Yeah.
Yeah, if it exists, it's unique, but
Yes.
This theorem tells us, like Alan said, if it exists or not.
All right, so to take our example again, the inverse of 4 mod 6 doesn't exist because 4 and 6 are not relatively prime. So let's try to take an example of this. So what is the inverse of 4 mod 5? 4 and 5 are coprime. Oh,
yeah, sorry, go ahead, Alan.
Oh yeah, in the chat we have coprime means that two numbers are coprime if their greatest common divisor is 1. Yeah. So now we'll try to find the inverse of 4. We have 4x is equivalent to 1 mod 5. Nice thing we can do here is to plug this into itself. We have 4x equals 1, so 16x is equivalent to 4. But this means, okay, I'm sorry. Oh right, sorry. Sorry, incorrect. That was 4x equals 1 multiplied by both sides by 4, till we get 16x equals 4. But 16x is equivalent to x because 15x is a multiple of 5. So we get that x is equivalent to 16x is equal to 4. So we have the inverse of 4 is 4.
Just in case the multiplication step wasn't clear, we know that we can multiply two things and preserve the mods. So if 4x is congruent to 1, then we chose to multiply by 4. Or yeah, you can notice that 4 is -1, so negative x is congruent to 1.
Yeah,
so we multiply by 4, and then 16x is congruent to 4, but 16x is just x, so x is 4.
Okay, so nice thing is that we can actually define fractions based on this. So just as in the rational numbers, 3/4 is equal to 3 times the inverse of 4. We have 3/4 mod 5 is equal to 3 times the inverse of 4 mod 5. That's going to just be 3 times 4, or 12 mod 5 is 2. All right. Ram, you want to take it from here?
Do you want to stop screen sharing, Alan?
Oh yeah.
Okay, so that covers modular inverses, and also Alan or Suyash, feel free to chip in if you want to say anything, as always. So yeah, we covered modular inverses. We went through an example, and now we're going to cover something called CRT, or the Chinese remainder theorem. It's a very important concept. We're not going to go through the entire statement of the theorem and everything surrounding it, but we're going to go through an example and see how it relates. So the first step is, well, let's say x is congruent to 3 mod 5. Here's a question for everybody. You might not see where this is going as of now, but it's leading up to something. So suppose x is congruent to 3 mod 5. Can you tell me something about what x mod 10 has to be? I'll give you guys a minute to think, and just put it in the chat just to Alan or myself. Don't put it to everybody. Think about it for a minute. What does x mod 10 have to be if you know x is congruent to 3 mod 5? Don't send it to everyone, just to one of the instructors. Yeah, some people are saying so. 3 or 8, that's exactly right. So the first examples of 3 mod 5 numbers are 3, 8, 13, because you add 5 at every step. That's preserving the fact that the remainder is 3. And these are all 3 or 8 mod 10, because you can see the units is usually 3 or 8. Can we generalize this? So let's say again, this is just an explanation for that, because basically if you're adding on, if you know x is 3 mod 5, so it's of the form 5k plus 3 for some k, integer k. If k is even, then it's 3 mod 10. If k is odd, it's 8 mod 10. And this quick algebra confirms that. So in general, let's say we know x is congruent to a mod m. So for example, 3 mod 5. Can we say something about what it has to be mod k times m for some integer k? So if we know what x is mod 5, can we say what it is mod 15 or mod 20? And basically what this tells us is that it has to be either a or a plus m or a plus 2m and so on. So this might be a little bit of notation right now, but basically it's just saying that in the mod km, we can sort of shift by m every time, and then it'll preserve the fact that it's always a mod m. So this is just telling us if we know it mod m, we can find a range of possibilities that it has to be for mod k times m. And the reason this is important is we're going to deal with something called linear congruences. So linear congruences are of the form ax plus b is congruent to c mod m. Now, you might have seen linear equations just in algebra before, where you have ax plus b equals c. But that doesn't quite, and there you can just say, oh, if ax plus b is c, then x has to be c minus b divided by a. But we don't know exactly know if the inverse exists or not. So that's been cleared up by the fact that we've covered modular inverses. But what if we have multiple linear congruences and we want to solve for it? So for example, when you have two lines just in regular algebra and you want to you want to figure out where they intersect, then you'd set both of them to be equal and you want to solve. So for example, does there exist an integer? So now we're going to deal with linear congruences and multiple constraints on a single x to see if it's possible. So does there exist an integer x satisfying x is 1 mod 2 and x is 3 mod 5? Now, I'm going to give you guys a minute to think. Please don't send things to everyone in the chat. I'm going to try and disable that setting just to one of the instructors. Yeah, so just, does there exist such an integer? What do you guys think? Also, if you have any questions at any time, feel free to unmute and just ask them. I'm going to wait for about 10 more seconds. Does there exist such an integer x? Now, as some people are saying, the answer is yes. For example, 3 works. Now, the reason what we were telling before is helpful is because from the first equation, x is 1 mod 2, what we're going to do is we're going to try and figure out what x is mod 10. And the reason mod 10 is because we can find out what x is a range of possibilities for x mod 10 using this equation and using this equation, since 10 is a multiple of 2 and 10 is a multiple of 5. So basically what we know is that from the first equation, we know that x is either 1, 3, 5, 7, or 9 mod 10. And the reason for that is it's pretty easy to see because, 1 mod 2 just means you're an odd number. And odd numbers either end, because we're doing mod 10, it just happens to work out that that's the units digit. Odd numbers always end in 1, 3, 5, 7, or 9. Similarly, 3 mod 5 numbers, like we said, they're either 3 or 8 mod 10. The reason we did mod 10 is because now we have a set of restraints on x mod 10 from the first equation as well as from the second equation, first equation and second equation. And previously we didn't have that. If you just look at this, we know something about mod 2, we know something about x mod 2 and mod 5. The only way to relate that is by considering the possible values of x mod 10. 10 is 2 times 5. So that's how you do this example. From the first equation, 1, 3, 5, 7, or 9, second, 3 or 8. And the only possibility that matches up in both of these, well, it's x is 3 mod 10. So what we've been able to deduce is that if x is 1 mod 2 and 3 mod 5, then x is 3 mod 10. Now, in general, CRT, or the Chinese remainder theorem, it sort of generalizes this whole concept. It tells us when there exists an integer x satisfying x is 1 mod 2 and x is 3 mod 5, and generalizing that. So say like 17 mod 30 and 29 mod 40 or something like that. And it turns out that such an integer x does not always exist. We'll go into more details about that in a later session, but it turns out that sometimes the lists that you write down, so for example, if you have 2 linear congruences and you write down the list of possible values in a different mod, and compare those 2 lists, it's possible that those don't have any common numbers. So here we were sort of quote unquote lucky, although obviously there's a deeper reason behind that, but 3 happened to be in both. So that's why x is 3 mod 10 satisfies it. In general, the method for, like I said, so the method would be if you want to have, say, x is a mod m1 and b mod m sub 2. Let's say you want to find x which satisfies a mod m1 and b mod m2. Well, is there a general method? The answer is yes. What you want to do is you can write down in terms of mod m1 times m2 or LCM of m1 and m2 because that's a multiple of m1 and a multiple of m2. You can write down a list of possible values for what x has to be mod m1 times m2 using this equation because it has to be a or a plus m2 or a plus 2 times m2 and so on. And then you can also write down using this equation. And since it's mod m1 times m2, you have a common modulus, which is really easy to deal with now. And now you can see if there's a common value in there. And then any value of x mod m1 times m2 is going to work. So that gives a sort of general method. I know we went over that really fast. We'll go more into that on a later week. This is called CRT, or Chinese remainder theorem. This sort of method. It's not really a theorem. The theorem tells us when it's possible, but the method is what's more important in general. So this tells us how to solve multiple linear congruences. And obviously you can do this with more than 2 linear congruences. If you have 3, then you can write down x is congruent to a mod m1, b mod m2, c mod m3. You can do mod m1, m2, m3, write those 3 lists down and see if they have any common numbers. Again, if you're confused about how to get the list, what I'm talking about, that's on this slide, the relating different mods. So basically how to get from, this is the important part, how to get from a mod m to a time to mod something bigger than m, or in particular something that's a multiple of m. So that gives us a general method for doing this. Yeah, Alan, you want to go through this example slowly?
All right, yeah. So
by the way, sorry, before we jump into that, my bad. Does anybody have any questions on that? I think let's take questions on this for, if you go back to the previous slide, Alan.
yeah.
Does anybody have any questions on this sort of linear congruence stuff that we did.
I know that it's been a long time, but what does mod mean again?
Mod just means that two numbers are equivalent mod if they leave the same remainder when you divide by the modulus. So
Okay.
if you're still confused, you can go back to the recording after the class or read the handout.
Okay.
Both
Does
of
anybody
those.
have any questions in specific on this though?
Is it, what is the condition that would make it so that there does exist an x? Could you briefly say that? Or
Yeah, sure. So that's sort of relating more to the side of Chinese remainder theorem. So somebody asked, in general, how do we know if you're given a set of linear congruences if there exists a solution? It's a little hard to tell exactly when, but if the moduluses are all coprime, if they don't share any factors, then certainly there exists a solution. There are special cases where there exist solutions in other cases, but here, for example, 2 and 5 are coprime, so you know there exists
okay,
a solution.
that's one condition under which
Yeah,
there will exist an x. Okay.
yeah, and this gives the method, which is more important. Alan, were you saying something?
Yeah. Any other questions?
Okay. Yeah. Any other questions? Let's pause for on anything we've covered so far. Feel free to just ask anything. Let's pause for about 2 or 3 minutes. Again, feel free to unmute. So somebody's asking in the chat, would we list the possible values of x mod m1 times m2 or x mod LCM of m1 and m2? The answer is it doesn't. You can do either. Basically, all you want is that the number should be a multiple of m1 and a multiple of m2. That way the lists will have the same modulus, and then you can see if there's any common numbers. So you can do either, but yeah.
Okay. Are we ready to go on?
Any other questions for anybody? All right. Again, if you're still stuck, you can feel free to ask in the middle or after.
All right. So this is another Amy problem. So our question is, we have another sequence of numbers. We know that A10 is 10, and we have this equation AN equals 100 AN minus 1 plus N. And we're trying to find the smallest n greater than 10, such that AN is a multiple of 99. So since we're looking for multiples of 99, we're going to want to work on this problem mod 99. So we're looking for the first AN, so n such that AN equals 0 mod 99. The nice thing about this is that AN equals 100 AN minus 1 plus N can simplify to just AN equals AN minus 1 plus N mod 99, since 100 is equivalent to 1. So now we can use that same pattern, that our same ideas, looking at small examples to try to find a pattern.
Alan, we want to go back for a sec, sorry.
Sure.
Now that Alan has said this, why do you guys want to take a few minutes and sort of think about what to do from here? We're going to give about four minutes.
Okay.
This is a hard problem, but yeah. Again, if you missed it, just take 3 or 4 minutes to go through this example. Try and so far what we've done, and try to finish from here. And if you have any questions, feel free to ask. Okay, we'll take about another 30 seconds. All right. If you have any questions, again, feel free to ask in the chat. But for now, you want to keep going?
All right, yeah. So looking at small examples, we have 10, 10 plus 11 is A11, 10 plus 11 plus 12 is A12, and so on and so forth. So we're seeing a pretty clear pattern that AN is going to be the sum of all the integers from 10 to n. So we would like to express this not as a sum, but as a more compact thing. So let's simplify it. We can actually say 10 plus 11 plus so on. It's going to be 1 through k, the sum of 1 through k minus the sum of 1 through 9. So that first part is going to be k times k plus 1 over 2. That's an important formula. And when you subtract the sum of 1 through 9, that's 45. We can expand to get this quadratic. And turns out it'll be really helpful to use k plus 10 and k minus 9 for this problem. Just factoring the quadratic. So why would that be? Because we want that product to be equal to 0, mod 99. Well, since it's 0 mod 99, it's got to be a multiple of 99. And a multiple of 99 has got to be both a multiple of 11 and a multiple of 9. Sure. Okay, just reviewing, somebody asked to scroll back up. So this is just reviewing. So since 11 times 9, as I was saying, is equal to 99, a multiple of 99 is going to be both 0 mod 11 and 0 mod 9. So what this means is that k plus 10 times k minus 9 must be 0 mod 11, as well as mod 9. What we get from this, in turn, is that either k plus 10 is going to be equals 0 mod 11, or k minus 9 is going to be 0 mod 11. Solving these gets k as 1 or 9 mod 11. Okay, any questions about this so far?
Yeah, just if I can say something, one thing that maybe wasn't clear is that from k plus 10 times k minus 9 is 0 mod 11. How do you get that k is 1 or 9 mod 11?
Right, yeah. So if k plus 10 equals 0, then k has got to be negative 10.
Right.
Yeah,
Basically.
and that's equivalent to 1.
Yeah, since 11 divides the product, since you know if something is
Right, yeah.
0 mod 11, then 11 divides it. And since 11 divides the product of k plus 10 and k minus 9, then you know 11 has to divide either the first one or the second one. And if 11 divides k plus 10, well, that just means that k is 1 mod 11. And if 11 divides k minus 9, then that means that k is 9 mod 11. So that's how we got those two cases.
Right. Yeah, so turns out we can use a similar method with mod 9. Since k plus 9 times k minus 9 equals 0 mod 9, we'll have either k plus 10 equals 0 mod 9 or k minus 9 equals 0 mod 9. This in turn means that k must be either negative 9 or 10. Sorry, negative 10 or 9 mod 9, or either 8 or 0 mod 9. So to sum all this up, we want we want k to be either 1 or 9 mod 11, and we want it to be either 8 or 0 mod 9. So this gives us 4 cases, and we can work through each one of these in turn.
Yeah. Does anybody have any questions about how we got to this point? Let's just pause for about 30 seconds, maybe. Yeah, like Alan said, once we get that k is 1 or 9 mod 11, and once it's 8 or 0 mod 9, then there's 4 cases for what k mod 9, comma k mod 11 is. And once, let's say we know k is like 10 mod 9 or like 7 mod 9 and 3 mod 11. Obviously, that doesn't happen here. Then using the method we described earlier, you can calculate what k has to be mod 99, because that's 9 times 11. But yeah, any other questions based on what Alan just said? Let's pause for maybe another 20 seconds. All right, if nothing, then feel free to keep going.
Okay. All right, we're going to test out each of these 4 cases to see what yields the least k, and that's going to be our answer. So case 1, let's try the first two. K is 1 mod 11, and k is 8 mod 9. So this gives a 1 value mod 99 by the Chinese remainder theorem mentioned earlier. Because since these 11 and 9 are relatively prime, we can test to find exactly one example. That example turns out to be 89 mod 99, because 89 is 1 mod 11 and it's 8 mod 9. So case 2, k is 1 mod 11 and 0 mod 9. Testing out similarly gives 45 mod 99. And the smallest value in this case is therefore 45. Our third case is if it's 9 mod 11 and it's 8 mod 9, we can again test our answer to find that it is 53 mod 99, and our smallest value is 53. If it's 9 mod 11 and 0 mod 9, then it's also going to be 9 mod 9. So we have it's 9 mod 99. You'd think it would be 9, therefore, but problem is that our smallest value was already supposed to be 10. So 9 doesn't work. Our smallest value is therefore 9 plus 99 equals 108. So of these, the smallest will be 45, and that's our answer.
Yeah.
All right.
Yeah. One thing that people maybe are saying they didn't understand. That's right. We did not actually go into the detail of for each case. We didn't say how to exactly find from 1 mod 11 and 8 mod 9 to say 89 mod 99. We skipped that part. That's omitted. But to compute that, what you need to do is write out all the numbers that are 1 mod 11 till 99, because you know we're going to find a solution mod 99. And in a separate list, write down all the numbers that are 8 mod 9 all the way till 99. We did not do that, so that's just omitted.
Yeah.
But there's no faster way. And then it turns out that 89 mod 99 is the only thing. So testing out, just as I was saying.
Chinese remainder theorem says there's only going to be one intersection for all of these.
The theorem tells us there's going to be one, but to find it, for each of the 4 cases, we have to write down those lists and then compare. And if you're still confused about what we mean by the lists, you can go back to where we covered that. But yeah, we do have to test out manually for each of the 4 cases. We have to write down the lists and find the common number, and then from there we can find out the minimum. So that part is just omitted. There's no quick way.
Ram has one last example for these concepts.
All right. Yeah, if anybody has any questions on the example that was just covered or anything else, we can feel free to take that as well in the remaining 10, 12 minutes. But so does anybody have any questions on the example Alan just covered or anything before? I'll wait for 20 seconds. Feel free to type it in the chat or unmute. Any questions at all? And one thing is that we're going to be releasing the handout for the class, which has these walkthroughs with greater explanation, as well as practice problems for you to do at home. They're in an increasing difficulty of order, so they start off pretty not too hard, and then they get to a harder level. So we're going to be releasing the handout after the class, as we're also going to release the recording for the class after today. You're going to get emails for when all that stuff is posted. And also the answers for last week's practice problems, we'll be posting those as well. We'll be updating the handout with the answers, and then again, we'll email everybody who's registered to with those updates. And yes, there's no homework that's due or anything, but the practice problems are extra practice if you want to work through those throughout the week. Okay. Somebody's asking what was CRT. CRT was just the method. So say in case 1, we had 1 mod 11, and 8 mod 9. So CRT is just tells us that CRT is Chinese remainder theorem. It tells us that there exists exactly one value mod 99 because that's 11 times 9. And remember, we have to multiply the bases, the moduluses. CRT tells us that there's one value which is going to mod 99, which is going to be 1 mod 11 and 8 mod 9. But to find that value, the method we mentioned is you need to write out the list, because a number is 1 mod 11 implies that it's either 1 mod 99 or 1 plus 11 mod 99 or 1 plus 2 times 11 mod 99, and so on all the way till 1 plus 8 times 11 mod 99. So you need to write out that entire list. Write out that similar list for 8 mod 9. So 8 plus 11, 8 plus 2 times 11, and so on. Sorry, for the 1 mod 11 list, I meant 1 plus 9, 1 plus 2 times 9, and so on, and then see what number is common. and then you'll find that that's 89, as Alan said. So yeah, just do that, and then you find it's 45. So you do have to do for each of the cases. Okay, if there are no other questions regarding that, then we'll do one final example. The question is this. N is this really big number, and it looks complicated, but it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is then written as 1, 0. Then 1, 1, 11, 12. So you write that entire number. So turns out it's 79 digits. You write out the number. And the question is, what is the remainder when n is divided by 45? So basically, the whole point of modular arithmetic is to deal with questions like this, where it asks for remainders, or when does, can you find the remainder of something when you divide by some other number? That's where mods come in. The concept is not very difficult. Like, there's nothing really that you didn't already know going on, but mods just formalizes all of that and gives us new theorems and ways to think about it. So I'm going to give everybody 2 minutes to think about this problem a bit, and then we'll come back. So let's try to work this out using all the concepts we've covered so far. All right, we'll give everybody about another 20, 30 seconds. All right. So the first step is the question asks, it gives us this number. The question asks, what is the remainder when you divide by 45? Now, the point of CR, so if we want to find something mod 45, then it suffices to find it mod 5 and mod 9. And then we can write out, let's say we figure out in some method that it's 3 mod 5 and 1 mod 9. Then we can do the method that's mentioned earlier. We can write out those lists to find out what's going to be mod 45. The reason we're doing this is because it's pretty hard to see, what happens when you divide by 45, but it's easier to see what happens when you divide by 5 and 9 separately, and then we can collate those at the end. So that's what we're going to do. So first, look at this number n. We can break it out. It looks pretty complicated, but we can write it using this method. So it's the problem gives us that there's 79 digits. So the first number is going to be 1 times 10 to the 78. So for example, like 1000 is 10 cubed. So 1 times 10 cubed. And then, so we're just going to write out like the base 10 expansion. So 1 times 10 to the 78 plus 2 times 10 to the 77, and so on until these first 9 digits. These first 9 digits, they just go down by 1 power of 10 each time. After that, 10 would be 10 times 10 to the 68 because this is 2 digits long. And then this is going to be 11. So that's going to be 11 times 10 to the 66 because we go another 2 digits down. So that's why you have to separate between the first 9 digits and then the rest, because we're going down by 2 digits each time. So 11 times 10 to the 66 and so on up till 43 times 10 squared times plus 44. And if you're not sure how we got this, then basically you can also work backwards. You can say, oh, it's 44 plus 4300, which is 43 times 10 squared, then 42 times 10 to the 4th, and so on. And then you can figure out these first 9 digits. So that's how you get this. And well, we can easily find what this number is mod 5. Remember, I said we want to find it mod 5 and mod 9. Mod 5, you just have to look at the final digit. So it's going to be 4 mod 5 because it's 4 mod 10 because the final digit is 4. So it's like 4 plus some multiple of 10, which means it's 4 plus some multiple of 5. So the number is actually 4 mod 5. And we want another way to do this is to say, once you have this expansion, we claim that 10 to the n is congruent to 10 mod 45. So that would basically say that all these powers of 10 go away. And you can do a bit of analysis to figure out, write out, once you figure out that 10 to the 10 is 10 to the n is 10 mod 45, you can write out what it should be and you can figure it out. But a quicker way would be to say, so it's 4 mod 5. Let's just look at the problem. Like I said, we want to find it mod 5 and mod 9, and then we can collate those. So mod 5, it's going to be 4 mod 5 because the final digit is 4, like I said. And mod 9, well, one trick you might know is to find a number mod 9, it's actually equal to the sum of its, a number is equivalent to the sum of its digits mod 9. You might have heard that in a way that, like 18 is a multiple of 9 because 1 plus 8 is 9, which is a multiple of 9. So basically every number is congruent to the sum of its digits. And then you can find the sum of the digits of this number. And the sum of the digits of this number you can compute. And then once you add those up, it's simply going to be something mod 9, and then you can collate. But here we're going to do a slightly different method. So we claim 10 to the n is congruent to 10 mod 45. To prove this, we can show that they're equivalent mod 5 and mod 9. So then by CRT, they'd be equivalent mod 45. So the latter, 10 to the n is congruent to 10 mod 5 is obvious because they're both multiples of 5. And so since they're both multiples of 5, they're both a 0 mod 5, hence they're equivalent mod 5. And to show that they're equivalent mod 9, well, we know 10 is congruent to 1 mod 9. And we also know that if we exponentiate this by n, then 10 to the n is congruent to 1 to the n, which is 1. So that means, and 1 is congruent to 10. So that means that 10 to the n is congruent to 10 mod 9, and 10 to the n is congruent to 10 mod 5. Hence, 10 to the n is congruent to 10 mod 45 as claimed. And from there, well, now look at the equation. Let's say we know that 10 to the n is congruent to 10 mod 45. Well, now you can just replace this 10 to the 78 with simply a 10 when you reduce mod 45 because, well, any n, it's just equivalent. So 1 times 10, and then similarly this 10 to the 77, if you do it mod 45, because remember, we want to find n mod 45. That's why we're doing mod 45. So 10 to the 77 is going to be congruent to 10 mod 45. Similarly, all of these powers of 10 are simply going to just become 10 when we reduce under mod 45. So what we're left with is 1 times 10, 2 times 10, all the way to 9 times 10, then 10, 11, 43, all the way to 44. If you don't get that, just look at this right here again. Just make all those 10 to those into 10. So, and we're reducing everything mod 45. That's what this mod 45 down here. And now to simplify this, well, you can pull out a 10 in front of all of these. So it'll become 10 times 1 plus 2 plus 3. And then remember, this is all just going up till 43 plus 44 because there's the 44 at the end. And we used this trick before. 1 plus 2 all the way till k for any k is k times k plus 1 over 2. So 43 times 44 over 2 plus 44. Now, here comes a little trick to make this a little simpler. You might say, oh, well, how do I compute this thing right here, mod 45? The numbers are really big. You could, you could just write out what it would be by multiplying, but that's not very fast. What you can notice is that 43 is congruent to negative 2 mod 45, and 44 is congruent to negative 1 mod 45. And that's simply because they're separated by 45. So that means that you can use modular arithmetic in this way. That this sort of shows you the power of modular arithmetic. Instead of here, you just have to multiply it out and find the remainder. You can just say it's negative 2 times negative 1, and then divide by 2. And similarly, plus 44 becomes negative 1. Remember, everything we're doing here is mod 45. That's why these are legal. You can't just say this unless you're doing the appropriate mod. And now you can just say, okay, -2 times -1 is 2, divided by 2 is 1. So it's 10 times 1 minus 1, which is 9. So that's one way to do it. Another way, like we said, is to, someone's asking what's the motivation for noticing that 10 to the k is congruent to 10 mod 45. The motivation is that once you see this expansion, let's say you're doing it this method, then these are really the bottlenecks here. The hard part is how do you deal with this 10 to the something when we reduce mod 45. And if you just notice that 10 squared is congruent to 10 mod 45 because 100 and 10 are separated by 90, which is a multiple of 45. Similarly, 10 cubed and 10 are separated by 990. Well, that's a little hard to see, but that's the motivation. 10 squared is congruent to 10, 10 is congruent to 10. Once you see that, you can simply exponentiate, and it's not very hard. Obviously, the other method to do this problem is to say, okay, mod 5, it's 4. It's 4 mod 5 because of the last digit. And if you know the trick about mod 9, you can say n is congruent to the sum of its digits, mod 9. So the sum of its digits, well, that's not very hard to calculate. It's simply 1 plus 2 plus 3 plus 4 all the way until 44, the sum of the digits. Well, actually not 44. You have to do 1 plus 2 plus 3 to 9, and then plus 1 plus 0 plus 1 plus 1 plus 1 plus 2 all the way until, you'd have to do a little calculation there. Once you find what it is mod 9, then you can collate those by using the CRT trick we mentioned, and then you can find it mod 45. So that's a different method. The method we presented here is a more straightforward method, in my opinion, because 10 to the, once you write out this expansion, you can just sort of work your way from there. So yeah, that ends this example. So let's just go over some logistical details. We're going to be uploading. Also, if you have any questions about any of what we covered, feel free to email us at pacificmathsociation@gmail.com. It's the same email you got the reminder for today for. The email is also on our website. We'll be uploading the handout, which has walkthroughs, the ones we covered, practice problems, and more. That's going to be uploaded sometime either today or tomorrow. You're going to get an email when that happens. The recording for this class will be uploaded also to YouTube. We have a channel that should be on the website. If it's not on the website, we'll put it there shortly. But the YouTube channel is where you can find previous recordings. That'll be uploaded sometime today or tomorrow. And we will also update last week's handout with the answers to the practice problems. Again, if you have any questions on anything, current practice problems will be covered in class. Last week's problems, anything, you can feel free to email us at the email mentioned. And yeah, if there's anything else, any other questions?
Thank you so much for coming to this.
Yeah, thank you everyone for coming. We're gonna end the class soon. But yeah, you're gonna get emails if you registered when everything happens. If not, just check the website.
Thank you.
Thank you. Bye.
Thank you. Bye.
Thank you.
Thank you.
Thank you.
Bye. Thank you.
Well, good job.
Wait, are Suyash and Nivid still here?
Nivid is.
Yo, Nivid, you wanna go on Discord? Maybe he's already there.
Yeah, sure. That's probably a good idea.
Okay.
Bye.
Bye. All right, we'll end the meeting now. Thank you for attending.